So let's just start with a what we left out the other day, but the last of the our integration method. Um, let's see, it's doing. Last thing we did is the rational functions, okay, using partial fractions. All right, so we've started with a couple of things, and let's do the uh, what the rational function itself. All right, so this is partial fraction decompositions. All right. So the idea is you would like to integrate, for example, do you see my cursor here? Or better, just
Yes, sir.
okay, here. For example, you'd like to compute this integration here. Okay, this function. Now it is okay. So suppose this 3x minus 1 over those x plus 2 x minus 3. That's if somehow we able to write this down as a over that x plus 2 plus b over x minus 3. Somehow this would be easy because this would give you a times ln plus b times ln. Right? So that's the reason why we would like to find that a and b. Okay, and this is called the partial fraction decompositions. All right, so that's the basic idea. Okay, so this is the last thing we did. Okay, so uh, let's do more on this one. Okay, so let's do this one here. Um, let's do this one using partial fraction decompositions. So what we are doing here is that look to see if you are able to write this down as this one here. So uh, that's equals to, well, we'll see, let's first factor this out, this cubic. Of course, we can first factor the x out. So you have x squared minus 2x minus 3. And we can further factor this out. X squared minus 3x, so x minus 3, x plus 1 there. Okay, so we have x here first, and then x minus 3, x minus plus 1. So this is a, b, c, where A, B, C constant. Okay, so let's find this ABC first, because if we find ABC, then this integral would be just ln of x, ln of x minus 3, and ln of x plus 1. Okay, so the main idea is just these decompositions. Okay, so let's do this one. Of course, I won't write this down, but what you have here, A, C, okay, x minus 3, x plus 1, bx, let's see, bx, this vector and this vector, and c, where c is, all right, cx, x minus 3, all right, okay, there we go. I want to write it down. Okay, so at the end, if you multiply this out, you should get 5x minus 3 plus 3. Okay, so let's try to find, but here you have a square here, right? So let's start. When you have square, you have, let's see, from here you have A. From this second term, you have B. From the third term, you have C. That's a square. And there's no square on the left-hand side, so that should be 0. And the x factor, see how many x you have here. You have a minus 2 here. So minus 2a. Here you have just b. Here you have just c. And that's equals 5. Okay. And what about constant? The constant should be, here you have minus 3. So here you don't have a constant from here, and you don't have constant neither from the third terms. So this should be 3. Okay. That's easy. A is -1. All right. So if you plugged it in -1 to first and second, you have a plus, sorry, b plus c -1. So there should be 1. And here you get b somehow this is inconsistent. How many x you have here? Minus 2a. This is, oh, made some mistake here. So from here, when x, the x term, okay, from here you have, let's see, if you multiply this out, you have -2x, so -2a. Yeah. Here you have x, bx, just bx from here, so b, and here you get see x times -3, so this should be -3c. Okay, so b minus 3c equals, okay, questions?
I have a question.
Aska?
Yeah.
Sure.
I still don't get how it's a plus b plus c equals 0, and then minus 2a plus b minus 3c equals 5, and then minus
All
3a
right.
equals like that
If you,
part.
all right. So if you want to do that, you just multiply this out. Okay. Okay. Multiply this out. You get some x square. You get some something from x and some constant from here. Okay. Now, but I didn't write it down. Even you don't need to. Just in the end, this should be equals to 5x plus 3 here. There. Okay. So this is what I do. Yeah. So there is no square here, right? But you have squares here. So I compute how many squares you have, how many x squares. Yeah. Okay. And the square comes from the first term, because the first term you multiply this out, you have x squared, so ax squared, right? And you multiply this out, you have b x squared, you have b, and you have c also from here. Okay, the first equations, first equality here, because there's no square. But if you compute x now, so from here, if you multiply this out, you have a negative 2x times a, so minus 2a. If you multiply this out, you have bx, just b. And then you multiply this out, you have negative 3 cx, 3c. So in the left-hand side, there's 5x there. Okay? Same thing with the constant. Okay?
Okay, sir, I get it.
Okay, right.
Sir.
Of course, you can proceed with long way, but that's longer. That be shorter if you just do this one. Okay, questions?
Yes, sir. I have a couple questions.
Uh-huh.
First question is, how do you get a x minus 3 x plus 1 plus bx, the long part?
Well, because you what you do if you're doing what's see addition of rational, what do you do if you have addition of rational? A over b plus c over d, what you do? So say 1/2 plus 1/3. What are you doing with this one?
You would try to match the denominators.
Uh-huh. What do you call this one? Over what? One half plus 1/3. So what do you need to put here?
6.
6. What is 6? Why 6?
Oh, the common denominator.
Yeah. And what you're going to put here?
3.
Top. 3. How you get that 3?
Because the one, oh wait, sorry, not 3.
Right?
It's
3 first, and then what?
3 plus 2.
There. How you get that 3? How you get that 2?
It's 1 over 2 times 3 and 1 over 3 times 2.
Yeah. Uh-huh. Same thing here. So what's the common denominator? Just multiply them out.
Oh, okay. No, I understand it from here.
Okay.
Right. So I do have one more question now. How do you get the x sorry, the one on the bottom left, like a plus b plus c.
Oh, if you notice a is -1, right?
Yeah.
So put this to here.
Oh, okay. Right.
Right?
That's all. Thank
And
you, sir.
if you put a plus 1 here, you get, let's see, this becomes 2, right? 2, move it to the right-hand side. So this should be 3. So you get 3 here. Okay. And then just subtract b, right? So b cancels. You get c minus 3c. So 4c equals -2. So here c is -1/2, and leaving b is, let's see, -1/2. b minus 1/2 is, so b is 3/2. Okay. So let's do the integrations now. In the end, you have this integral 5x plus 3 x minus 3 x plus 1 dx is just, let's see, this is a minus 1. So this is -1 x over x, and b is 3/2 dx over x minus 3 minus 1/2 integral of x plus 1. There you go. So what you have here, this is negative ln of x, absolute value, and then 3/2 of ln x minus 3, absolute value, minus 1/2 ln of x plus 1, not c, just k, constant. And if you would like to somehow simplify this one, because this is addition or subtraction of ln, you put this as, let's see here what's the top. So x minus 3 power 3/2 over x. Yes. Okay. Okay. So in this case, the integral, the calculus is easy actually. The more important is how you write this down, how you decompose the integrants. Okay. So that's the basic idea. See here. So that is the case if you have distinct linear factors. All right, so let's do the next one. Next example is, this is distinct linear factors. So you should do this one here. Okay. Now, what you do with repeated linear factor? So linear factor is x minus 3, but it's repeated because it's a square, right? X over x minus 3 squared. So let's do this one. So that is the case. Distinct linear factors. Now let's do this one. Compute x, 3x over x minus 3 square dx, for example. Okay, so let's do this one here. So let x minus 3. All right, but this is a double factors here. So you get, is there, okay. Is it possible to do this one here? Well, if you do this one, you get, well, there's no common factor because if you multiply this out, you get nothing like this. You have, right? Because they are the same. And there is no way it's going to be the same as this one. Why? Because this is square, this is x minus 3. Okay. Okay. Left hand side equals to, because they are different denominators. And if you insist to and you get something like this. And if you insist, then of course you can make it square, but you multiply this out with x minus 3. Okay. And you see, just as the one we did above. So we have, let's see, we have, now we have a plus b, because this is a plus b times x, right? So this should be equals to 3. Okay. And then a plus b here, negative 3a plus b equals to 0. Okay. So from here you get a plus b equals 0, because negative 3 times something, that should be 0. Then there's something should be 0. But if this should be 0, then this it would contradict this one. Okay. So this is impossible to do. Okay. So in fact, the correct way to do this one is this one. Okay. To do this one, and look like this one. Okay. Now, if you proceed, common denominator, of course, this is a common denominator. Okay. On the top, you should get this plus b. Okay. Now from here that you get, all right, so let's multiply this out. You get some x and then some constant. So for x, you get, here you get just a, right? That should be equal to, on the left-hand side, you get 3. Okay. And then the constant, you have here, let's see, minus 3a plus b. That should equals to 0 because no constant here. Okay. And if you solve this for b, this is 3, this is negative 9. You put it back here. So here you have b equals 9. Okay. Then the integral is just this integral. The yeah. B. So in here you get 3 ln. But in this case, you should get, let's see, just write it down. This is substitutions. U equals x minus 3, right? So that's easy. And du equals dx. Okay, so you should get 9 over, let's see, this power, it should be integral of u minus 2 du. Okay, so then you should get negative 9 because over negative 1, u minus 1. 1 over okay, so this is what you mean to get. Questions? Okay, so this is how you get with the repeated linear factors.
No, why is the 9 negative?
9 negative because you get 9 over negative 1 here. Okay.
Okay, I get it.
So this is the case of repeated linear factors. And you can combine repeated and some distinct. I'll just show you from directly from the textbook. This is repeated linear factors. Some distinct, some repeated. Okay, so for example, on the denominator, you get this one here. So the distinct x plus 3, x minus 1, but then the x minus 1 is double because you have square here. Okay, so the decomposition should be x minus 3, x minus 1, and x minus 1 squared, because x minus 1 is repeated twice. Okay. And so you have to now you equalize this one. If you multiply this out, how many? Get 8 times, let's see, this one, x minus 1 squared, and b times x plus 3, and x minus 1, c times x plus 3. Okay, so the square should be 3, the x's should be negative 8, the constant should be 13. Okay, and you can just solve it using let's see, use maple or whatever there. Just use, I'll show you with maple. Okay, so what it should be here? Let's compute this one here. So here you have the square. How many squares do you have here? So from here you get a. The second term you get just b. And the third term's no squares there. So then that should be 3. X term. The x should be, here you have negative 2, so negative 2a. Here you have, let's see, just 2x, so 2b. And here you have just c. That should be negative 8. And the constant should be, see how many here? Just, 1, so just a. Here the constant is negative 2, so negative 2b. Here the constant is just 3, so plus 3c. That equals 13. Okay, if you try to solve then using that one, let me just do using Wolfram. Of course, this is still easy to solve actually, but I just want to show you that we can do this using the computer algebra. Okay, where's my Wolfram? Yeah. So here you just solve in the set parentheses a plus b equals 3. Plus b equals 3, comma, a plus 2b plus c equals negative 8. And the third should be, oh, sorry, a minus 2b plus 3c equals 13. Ah, wrong. Cancel. I mistakenly put this one. Connected problem. So let me move this to Wi-Fi. A plus B equals 3, correct? Oh, put wrong method. Uh, no, I may make mistake because it should be a bunch wrong number here. It should be plus C equals to 13. All right, let's continue with this one here. You should check whether you should get this one, but I suspect there's something wrong here. Okay. All right, so let's find this out how to get these things simpler. Right. So let's make at least one of these 0. The thing is, plug in here just x equals 1, for example. Okay, so if you plug in x equals 1, and this would be cancelled, right? X equals 1, that's 0. X equals 1, this is 0 also. So you get only here 1. So for C equals C, just plug in x equals 1. You get 3x. Let's see, 1. So 3 minus 8 plus 13. Okay, plug in x equals 1. So you get, let's see, how many of this? 13, 16. So just A equals 16, right? Sorry. How many? 3 times, oh, sorry. Yeah, 8 plus 13. So that's 16 minus 8. All right, so this 8. Yeah, 8. So C plus 2. Okay, and if you try to plug in x equals -3, so this cancels. Right. So you get what you get here. If you plug in 3, -3, you have this cancels also. This 0, this 0. So you get only -3, -4, so minus 16a. Equals, if you plug in -3, you get 9, plus 8 times 3, 24, plus 13 equals okay. This is 40, 51, 64. So A equals 4, remaining B. And find B, let me see, B equals -1. Okay, in the end, you have this. Okay. Somehow check this one, please check this one. Because if I plug this into Wolfram, this should be, it should give to A equals. Now, this is something that I believe is not correct. Why this? What's wrong with that one? I'll check that later. Okay. All right. So that's the combination of linear, distinct, and repeated factors. Okay. All right. So let's see if you have something like you decompose this one here. For example, this. Okay. So here the linear factor should be 4x plus 1. Okay. And x squared plus 1, there's no way you can simplify this further. So this is the what we call the non-factorizable. Okay, so this, so you just put it there. Okay. All right. So what you put in at the top. So this, because it's linear, so this is a just a. Okay. Because this is a square, you put linear there. Okay. So just bx plus c. Okay, and if you multiply this out, you get this one. Okay. And using this, you solve this, you get this. Okay. So you get this one. All right. Let's do some more example and just do the from the exercise. Okay, so what about this one here? Some linear factors and quadratic, but the quadratic is repeated. Okay, so you see, so this is linear. This is quadratic. This is quadratic repeated. Okay, so you get this A because this is quadratic. Then this should be a linear one. So bx plus c. And here's quadratic, so you have to be linear here. So dx plus e. There we go. After considerable work. But you can solve this one. Okay. All right. So that's the idea. That one here. Okay. All right. So do you understand the logic? Now let's do this one to some of this problem here. Some example. Okay. For example, let's do this one here. We'll just do the decompositions, not the integral. Okay. So 2 over x squared plus 3x. That's some examples. So here that's easy because if you can factor it x, okay. So just mention the case. What's the case? Distinct linear factors. Okay, and here you get x plus 3 there. Okay, that's the other example. Uh, Factors. All right, so let's see this one here, 4. So 5x over, so we get 5x x cubed. Okay. So the denominator you can factor x square. Okay, so you leave with 2. Oh, you should factor 2x squared instead, the constant. So you get x and then 3. Okay. So here we have, what's the case? What's the case for this one? How you should decompose this one?
Do you just split 2x squared with the bracket, sir?
Split, so what do you mean? Split the x with the bracket.
Yeah, so the first fraction has a denominator of 2x squared and the second denominator is x plus 3.
And what do you put on the top?
A on the first denominator and bx plus c on the second one.
A. Here you have bx plus c.
Yeah,
Let's see. If you do this one, the integral, for example, this one here, the integral would be, let's see, what's the integral for the second? Suppose you get b and c. Because if you compute this one, you get, let's see, let's just proceed with this one. If you compute this one, you get 8 times what?
x plus 3.
Plus times,
2x squared.
okay. Let's just follow so we can see what it leads to. Okay. All right, so this is the same denominator, so you have to equalize the top, right? Okay, so how many do you have here? Okay, here you have, oh, you have a cube here. All right, so that's, it doesn't matter. If you have a cube, let's see how many cube you have just from here, right? So 2b. And there's no cube in the right-hand side. Sorry, yeah, left-hand side, so that's 0. How many squares you have? There's no squares here, and you have let's see, so c times 2x squared, so 2c. No squares, that's a 0. What about x? How many x? Now x from here, but you get x from here. Just a. That's 5. Right? And what the constant? Constant should be, what's the constant?
3a.
3a.
3a equals 0.
0. So what you get from here? That's a equals 0, right? So b equals 0. C equals 0. Right? So what's wrong with that one?
Maybe switch the numerators, sir, so we don't get a cube.
Which denominator? So what you propose here equals what?
Exactly the same, but we switch the numerators. So
Switch here. Uh,
bx
okay,
plus
let's do this one. So you know what's wrong with this. Let's just do. You mean there? Okay. Why do you want to switch?
so that there's no cube.
Right. The idea is because if you have irrational functions, uh, uh, let's see, if you have rational functions, so px over qx, okay, in this case, we should have degree of p less than degree of q, right? Now, if this is, why? Because if you have the same degree, you just long divisions, or even degree p is greater than degree of q, then just long divisions, right? So you got polynomial over, and you work is a remainder. See, I think I mentioned that last time. All right, so that if you have something like this, and then degree of p is at most degree of q minus 1 less than degree of q, the denominator. So if you have a square, then this should be linear. If you have linear degree 1, then you have a constant degree 0. If you have the here degree 5, then you should have degree 4 on top. Okay, and that explains why this doesn't work. Because here you have a square, but you put a constant there. Here you have power degree 1, but you have degree 1 also on the top. That tells you why it doesn't work in this case. Okay, so while this one, at least at the moment, this is correct because this is a square and the top should be a linear, should be power degree 1. Here degree 1, then the top should be degree 0. Okay, so this might work. Let's see. Let's do this one here. And you should get ax plus b times what? X plus 3 c times, oh, so just directly, yeah. Okay. All right, so you see that now you have, let's see, power 3, you have power 2. Okay, so you square, compute the square, you have how many squares you have? A from here, from the first term, and here you get to C. Then that should be none on the left-hand side, that's 0. Only x, you have, here you have, let's see, 3a plus b, right? From here, the x comes from this one. So a and also this multiplications. Sorry, with this one. Okay, so ax times 3. So 3a is b. Right here, no no x. So you have this 5. And here the constant. Let's see, how many constant there? No, 3b. Here, no constant. That equals 0. Okay. Then this b equals 0. So a here is 5/3. C is let's see. C here is minus a over 2. Okay. So it is possible to do this one. So then that
Sir, I have a question.
equals, sorry, let me just finish this one.
Okay, okay.
5/3 x plus, oh yeah. Okay. So when you integrate, you get ln from here, you get ln from here. Okay. All right, so this works. All right, your questions.
Yeah, why is it ax plus b plus c when not just a plus b?
Not a plus b.
Yeah, was
Did
it
you
not
say?
a over 2x squared plus b over x plus 3? Not, and why is it ax plus b over 2x squared plus c over x plus 3? Like, why is the
Let me see.
numerator ax plus b and c?
Which one? Numerator ax plus b. Oh, this
It's
one?
yeah.
Uh-huh. Well,
Oh, why is
because,
it like that?
well, the thing here is this is a square, right? So you gotta have a linear on the top. What's the general rule for linear? Or degree 1, power 1. So here's ax plus b.
So if it's x cubed, is it a quadratic on top of it? Is that
Yeah.
how it works? Okay,
So
okay.
this is x cubed, then you have ax squared plus bx plus c.
Okay, thank you, sir.
But there is another way to, I mean, an easier way to do this one. This is correct. But there is an easier way to do this one and more systematic. So let's see, this 5x. What's 2x squared? Okay. Let's see the case here we have. Here you have the linear factor just x, right? But you have square. So consider this as a repeated linear factor. Okay. Well, this one is distinct. So this is a combination of distinct and repeated linear factors. So in that case, that should be, this is just x, okay? The repeated, because this is repeated. And the distinct one, just put there. In this case, this should be just constant. Okay. Do you see what I mean? All right. So in general, you have a cube on the top. Cube on the top. So you have at most here a square on the a cube on the bottom at the denominator. So you have a square on the should have a square on the top numerators. And a squares in general, that's ax squared plus bx squared plus c. So you have three parameters a, b, c. Now, we don't need to put bx plus c here or bx plus d because otherwise you have four parameters. Now, the number of parameters should match. You have three and you have three also. Okay, so this is the easier one. Okay. Not I would say easier, but it's more systematic how you deal with the repeated factors, how you deal with the distinct factors. Another example, what if I put something like this? And how do you decompose this one? This is repeated. This is distinct. What you do with the repeated one? This is repeated 3 times. So the first one, second one, third one. Okay. So this is just put A, B, C. What about the distinct one? You just put there separately. Okay. So although this is correct, no. Oh, this is incorrect. So I guess although this is correct, right? But it's not as systematic as this one here. And they should be easier to integrate. This is ln, and it's just 1 over x. Okay. Questions?
Sir, sorry, can you repeat? Why don't you put a bx over x squared?
Bx over here. All right. So the idea here is just a all right. Okay. The idea here is that of course you can replace this by something like this, for example, Vx plus D. Okay. And you have C here. That makes sense because this is square. But later on, you see, when you have something like this, multiply this out. Okay. All right. So sorry, just square. So you have a power 3 here. So you should have a square here. So a square should be C there. Sorry, C tilde in general. So how many parameters you need? 1, 2, 3. And if you put this bx plus d, you should get 1, 2, 3, 4. Now, the too many parameters, that's okay here, because this will be 0 anyway later on. So you don't need this d, just put it b. Why? Because if you multiply this out, right, so you get there. It's already there, ax plus b in this case. Okay.
Okay, thank you, sir.
Right. So basically, we write this down as replacement for this one. You split the x and x squared. You get this one exactly. But this way, you know how to deal with the distinct and repeated factors differently. And you have a, say a factor 10. So you should just x squared, x cubed, x to the 4th, until x to the 10th. It might be long to compute, but it works. Okay. And the same thing for what we call for quadratic factors. All right, so let's just mention the case. This is distinct factors, linear distinct factors. This is, let's see, can we? Yes, we can. This is also distinct linear factors, because this we can factor as let's see, plus 3 minus 2. Yeah. So 3 distinct factors. But what about this is the case of repeated factors, repeated linear factors. Okay. Let's see. All right. This is linear factor. This is a quadratic, which you cannot factor anymore. Okay, so it's quadratic factors, power 1 here. So this one should get to x minus 1a plus, okay, but because this is a quadratic, then you should get something like this. Okay. Let's see. All right. Let's see this one. Okay. This is a non-factorizable quadratic, but it is repeated. So you have to get to have this one. There. And because this is quadratic, then it should be ax plus b, and then cx plus d. So that's how you decompose this one. Well, this is with the trig functions, but actually, this is polynomial in term of trig, cosine, in term of cosine. Okay. So that's the idea of the partial fractions method. So the difficulty stems from the algebra, not from the calculus. The integral is easy. All right. So this I mentioned about strategies of integrations. First, always look for substitutions. Okay, substitutions. And in particular, choose u so that the derivative of u, the multiple of derivative appears in the integrand. For example, here we choose u equals minus x squared or just x squared, because the derivative 2x is a multiple of the other term. Here you can choose x squared plus minus 1, that's u, because the derivative 2x is multiple of this x. Right? So it is a product of function and the in differential, then use integration by parts. Trig substitutions, so this one. And rational functions, that's the partial fractions. Okay. All right, I'll show you the how to deal with maple. Okay, with this maple, let me just the in the instructions is easy, just int to int. For example, the last thing we did is 5x over what's x squared, so 2x squared times what's the x plus 3. Okay, you integrate with respect to x. There. So let's give you the answer already. Okay, and you can do also definite integrations, say from 0. Let's see. So from 9 to 11, for example. There. It's definite integrations. Okay. So let's use maple. The thing is, we cannot compete with these machines. All right. So the method integration that we learn is only to give you an idea how to do integrations, okay, and look up from the table. Okay, so just checking. All right, so let's pick some problems here. Do you see, can you see both of the maple and the textbook?
Sir. Yes, sir.
All right, so let's do this one here. What's the exercise? Right, for example, all right, problem 10, for example, here. 10, so integral of 1 over, let's see, e minus square roots. The square root is QRT, for example. Square root of 2t. T equals 3 to 4. There, good. See. Okay, and you can use this maple or wolfram. You can have a wolfram in your Android or an iPhone. Okay, solve it. Okay. All right, that's what I'm trying to do. All right, so then let's take a break for 5 minutes and we'll start with the next chapter, new chapter of this. Just take a short break.